In this video, we'll be solving a few examples of some irregular linear programming problems. Let's take a look at our first example. We're given an objective function and several constraints, and our goal is to find the optimal solution. Since this problem only has two decision variables, we can solve it using the graphical method. So our first step will be to plot each of these constraints on our graph. Our first constraint is 3x1 plus 2x2 is less than or equal to 18. And for now, we'll disregard the inequality sign while plotting. We can find the intercepts of our first constraint. So if x1 equals 0, then 2x2 equals 18. So x2 has to equal 9. And our other intercept is if x2 equals 0, then 3x1 equals 18, so x1 equals 6. So labeling our graph, we can plot each of these points. We have 0, 9, and 6, 0. We'll connect these dots, and that's our first constraint. For our second constraint, x1 plus 2x2 is less than or equal to 10. We follow a similar procedure, and we get our intercepts to be 0, 5, and 10, 0. And we can plot each of these. That's 0, 5, and 10, 0. Our next constraint, x2 is less than or equal to 4, is just a horizontal line that intersects at x2 equal to 4. And we have our non-negativity constraints. So x1 and x2 are greater than or equal to 0, meaning it's in the first quadrant. So that gives us all of our constraints on the graph. Now we can deal with our inequalities, and since all the constraints except the non-negativity are less than or equal to, we know that our feasible region must lie below all of these lines. So the region I'm shading in will be our feasible region. And this is bounded by several boundary points, which I'll start labeling. We have point A at 0, 0, point B at 0, 4, point C, which appears at 2, 4, then point D, which is at 4, 3, and point E at 6, 0. So now we have to plug in each of these extreme points into the objective function and find which point gives the highest value, since this is a max problem. So point A is at 0, 0. That gives a z value of just 0. Point B is at 0, 4, which gives z equals 60 times 4, which is 240. Point C is at 2, 4. So z is 30 times 2 plus 60 times 4, which is 300. Point D is at 4, 3. Which gives z equals 30 times 4 plus 60 times 3, which is 300. And point E at 6, 0 gives z equals 30 times 6, or 180. Among these points, we have to choose the one with the highest z value, except in this case, point C and D both have the highest z-value, which is 300. So in this case, we have what's known as multiple optimal solutions, because we have 2 points, namely C and D, which have the same z-value, which means that any point along the line CD will give an optimal solution to this problem. And the reason for that is, if you look at this constraint, x1 plus 2x2 is less than or equal to 10, the slope of this constraint is equal to negative 1/2. And if you look at the slope of the objective function, it'll be negative 30 over 60, which is equivalent to negative 1/2. And so since these slopes are the same, there's a good chance that there's going to be multiple optimal solutions. So it's just something to keep in mind when solving these problems. If one of the constraints has a slope that's equivalent to the slope of the objective function, there's a chance that there will be multiple optimal solutions. Let's take a look at our second example now. As always, we begin by plotting the constraints. So our first constraint, we have intercepts at 0, 50 and 25, 0. And we'll connect the dots. That's our first constraint. Our next constraint, x1 plus x2 is greater than or equal to 60. Our intercepts are at 0, 60 and 60, 0. And connect the dots once again. Our third constraint is x2 is greater than or equal to 30, which is just a horizontal line intercepting at x2 equals 30. So when trying to find the feasible region, looking at our first constraint, we have a less than or equal to sign, meaning we have to be below this blue line here. Similarly, when we look at the second constraint, it has a greater than or equal to sign, meaning we have to be above the green line. However, if you notice, it's not possible to be below the first constraint while also being above the second constraint. So if we take a point inside this blue region here, that means it satisfies the first constraint, but it doesn't satisfy the second constraint. However, if we take a point inside the green region, that means it would satisfy the second constraint but not satisfy the first constraint. Because we have no points that can satisfy all of our constraints, we have an infeasible solution, meaning that we have no optimal solution to this problem. From a practical standpoint, if we ever have an infeasible solution, we would need to change some of the constraints or resource quantity values in order to get an actual solution. Moving on to our final example, we begin as usual by plotting each of our constraints. So starting with our first constraint, we have intercepts at 0, 40 and 20, 0. So connecting those two dots, we have our first constraint. Moving on to our second constraint, we have intercepts at negative 20, 0 and 0, 15. And our third constraint, we have intercepts at 0, 20 and 30, 0. So in finding our feasible region, we have to look at the inequality to see which direction we have to shade in. For the first constraint, we have to be greater than or equal to, so that means we must be above the blue line. The second constraint, we have to be below, and the third constraint, we have to be above. So putting all this together, our region will look something like this. So something to notice about this region is that it's unbounded. We do have boundary points, but this region itself is not closed. We can continue shading in the region indefinitely. And this plays a role when we're trying to find our optimal solution. So if you look at a few points inside the feasible region, let's say we look at 30, 0, then the z value will be 100 times 30, which is 3,000. So now let's take another point inside the feasible region. Let's say 50, 0. Then the z value will be 5,000. So if we continue increasing our value for x1, then our z value will continue to increase. This means that we can continue to increase z for as long as we want. So this means we have an infinite profit. And because of that, we have an unbounded solution. Just as a side note, if this was instead a minimization problem, we would have an optimal solution and it would occur at one of the boundary points of this feasible region. Just to recap, we covered 3 examples of irregular linear programming problems. We did an example with multiple optimal solutions, an infeasible problem, and an unbounded problem. Thank you.